you can pick it up on Wednesday if you want. If you didn't score too well, like, please do this thing that I posted, which is just just read the solutions and then kind of redo it on your own words and then post it on Gradescope. It's not to like give you back points, but later on, like when we're making the final thing, I'll help you out. Okay, so. And if you do well on the final and the second midterm, we can also talk about some other ways to help you out. But like I said, I mean, it doesn't cost me anything to give everybody an A, right? So it's like for free for me. So if you do well on this last two, if you're not happy with how you did, there's still time to improve and some extra work that you can do. Okay. All right. So let's get started. Yeah. Yeah, so why don't you wait till Wednesday, and then I'll give the TAs the test, and then you can, like, if you go to your discussion sections, they'll have your test, and then you can talk to them then. I did have office hours today, so some students also came there. I only have to wait until the next office hour, so. And the TAs also have office hours Monday and Tuesday, so I'll make sure they also have the test there, so you can go there as well. Okay, so now let's talk about some fun stuff. Bellman-Ford. So what did we do last time, right? Last time was I gave you a graph, and it was like it was an unweighted graph, and I said, okay, given a starting node S, right? If I run BFS, I can find the shortest paths from this starting node to all the other nodes, okay? So that was the power of BFS. But now we're going to talk about a different algorithm that can do more, okay? So now, what if the edges have weights? So imagine like you're driving, right? It's not just that every road is 1 mile, but every road has like a certain amount of distance, right? And you still want to find the shortest paths, okay? So for this lecture, right, we'll have a graph, n nodes, m edges, but every edge will have a weight, okay? So the weight sort of represents the cost to like travel on that edge, okay? So some edges may be more costly than others. Yeah, so just to recap, like if we didn't have any weights, then we already solved this problem, right? We had this algorithm called BFS, or the BFS algorithm. In linear time, right? It just looked at every edge all of one time, and if I give you a starting node, right, it told me all the ways to go from that node to every other node. In short, yeah. Yes. Oh, okay. Sure, yeah. Let me do it right now while I talk. Okay. Like I said, right, this BFS algorithm is really powerful. But the one downside of it is that it doesn't handle weights, okay? So, okay, what am I doing? Oh yeah, I'm putting up the files. Give me 1 second. Yeah, this should be it. Give me 1 second. So, what is this? This is lecture 9, I think. October 2nd. Okay, yeah, it should be there now, the slides at least. Yeah, okay, but there's a part where we're going to go to the board, so that I have it handwritten, so I can't. I'll do it later. Okay, but now we want to handle weights, okay? And this is like a non-trivial problem because like things that have few hops may not actually be really good paths to take, right? Because the weight could be super large. Okay. So the rest of this class is about this really nice algorithm called the Bellman-Ford algorithm. It's named after two people that invented it at the same time in the 50s. That roughly takes O of m times n time, right? So what it does is if I give you a source node, a node in the graph, it'll find me all the, and this graph is weighted, it'll find all the shortest paths from that node to every other node in O of m times n times, okay? And yeah, if you ever take like a reinforcement learning class, you'll hear this person's name, Bellman. if you heard of like Bellman equations or whatever, it's the same guy, like the same dude. Okay. All right. But now I say, right, now the graph can have both positive and, can have weights. And the weights actually can be both positive and the negative weights, okay? So the intuition for why you might want negative weights is, let's say there is, traffic also, right? And some roads don't have traffic, even if they're long. So you want to like help them out, right? You say, okay, if it doesn't have traffic, maybe like it has negative weight. I actually want to go on these edges, okay? Or you can think of it like some roads have tolls, right? And the roads that don't have tolls, right, they have negative weight because I'm incentivized to go on them, okay? So in general, I just have a graph. The edges can be both positive and negative weights. I give you a node, and I want to find the shortest way to go from that node to all the other nodes, okay? So that's the problem. And Bellman-Ford is an algorithm that solves this in m times n time. And the cool thing is, like, this is still the fastest known algorithm for this problem. And it's been here for like almost 75 years. That's pretty cool. Okay, there is one caveat though, which I say, which is like, if I'm allowing the graph to have weights that are like less than 0, negative weights, then you could have this like kind of silly edge case where like there's a cycle that has total negative weight. So actually the best shortest path is not defined, because you can just keep going on this loop over and over again, and you keep like accumulating negative distances. So we're going to have to be careful to like kind of figure out when this happens and kind of rule that out, okay? But yeah, that's like one edge case that happens when I'm allowing negative edges, is I can have like cycles that have negative weight, okay? Like here, if I go from 0 back to 0, right, I pay minus 2 cost, right? So I can just keep going back and forth. So the shortest path is actually like negative infinity, right? I can get as negative as I want, okay? So we're going to have to, somehow the algorithm is able to like figure this out and say, okay, if it says there's a negative weight cycle, then it says, okay, actually the shortest path doesn't make sense here, and stop, okay? So it'll also do that. But of course, there are other cases where, right, you can have negative edges, but you won't necessarily have a negative weight cycle, okay? All right. So now let's talk about the Bellman-Ford algorithm. It's actually a very intuitive algorithm, but I need to define some notation first. Okay, so right, I have this graph G, right? It has some vertices, some edges, and this W is just the weight. Okay, so if W of u comma v is the weight of that edge, and just for like convenience, I'm going to define this notation delta s comma v. So s is like the source node. Okay, so that's always fixed. So I give you one source node, okay? That's the part of the input of the problem. I have one source node that I care about. And then, right, I want to compute delta s comma v for all the other vertices v, okay? So I'm just going to define that to be the shortest path distance, okay? So I'm just going to have some name for it, okay? Some notation. And the goal is, right, compute these shortest path distances for all the other vertices, okay? So that's the problem. All right, so does the problem make sense before I talk about the, how to do it? Any questions? Yeah, if something doesn't make sense, happy to go back. Okay. All right, so let me kind of like motivate how someone would come up with this the algorithm, right? Because if I just tell you, like, okay, I give you a graph with negative weights, positive weights, find the shortest paths, it's not so easy to think about solving this problem, right? Like, because there's so many paths to check, right? You have negative edges, so like actually a longer hop path can actually be better for you because you can use a negative edge. But the whole idea behind this Bellman-Ford algorithm is very intuitive. It's going to keep making sort of like local changes or local improvements. And the cool thing is somehow if you do enough local improvements, then you get a globally correct answer. Okay, so that's the power of this Bellman-Ford algorithm. So the main idea, like I said, is to do local improvements. And the algorithm is going to run in different rounds, okay? And at every round, it's going to have an estimate of the distance to some vertices, okay? To all the vertices, okay? So I'm going to call that by v dot d, okay? So at some round, right, I have some estimates to all the distance to all the vertices. Initially, it's infinity, right, besides the source, because I don't know anything, right? Initially, all my estimates are very, very large, okay? And now the Bellman-Ford algorithm is going to make local improvements by doing the following. Okay, so forget about the words. Let's just look at the picture. Okay, it's going to use this operation called relax. Okay, so what is the relaxing operation? If you've ever, it's kind of like related to this triangle inequality, if you heard of that. So what is the relax operation? Is I pick an edge, u comma v, and I say, okay, this edge, right, points from u to v. And now what do I do, right? I look at the distance that I have so far to both u and v. Okay, if I say, okay, if there's a way to make the distances to v better by going through u, I'm going to update that. Okay, so if there's a way to sort of, let's say I have some path, right, currently in my algorithm as is running, that goes from the source to the vertex v, okay, with some distance v dot d. What I'm going to do, I'm going to say, okay, let me look at all the ways to go immediately to v through some node u. Okay, I'm going to say, okay, if I go to u and then take the edge, if that's a better estimate than what I currently know, then I'm going to update it. Okay, so that's what this relax operation is doing. Right, I'm going to pick some edge, and right, the edge goes from u to v. If I notice, oh, I can get to v faster by going through u, the current estimate I have through u, and then hopping on this edge, then, and if that's better than the estimate that I'm keeping for v currently, I'm going to update it. Okay, so if I can make this local improvement, I'm going to do it. Okay, so that's the relax operation. It's I take an edge and I say, okay, can I use that edge to help me get to that endpoint better? Okay, so that's like this. So this is not a complete algorithm yet. There's this one like key subroutine. All it's saying is, if I can sort of shortcut through u, then I'm going to do that, if that's possible. Okay, so that's what this operation is saying. Any questions about this relaxing? It's sort of like making sure that the triangle inequality is not violated, right? Like, when you think about distances, right, like going straight to something should be faster than like going roundabout in a roundabout way, right? So that's what this is making sure, right? If it's the case that going straight to v is slower than going through some intermediate node, then I'm going to update that. I'm going to say, okay, you know what? I'm going to go through this intermediate node instead than what I know currently. Okay. Okay, so this is a fundamental, and I mean, I haven't shown you the full algorithm, but this is the key piece of the algorithm. Okay, this is a local improvement for an edge. Okay, like where essentially you're saying the triangle inequality is not violated. If somehow whatever estimate I have that I had to go from S to V is worse than going through some other intermediate node U, I'm instead going to go through this node U. Okay, that's what this is saying. Okay, so right, in kind of like math, right, it's saying if the current estimate I have V dot D is bigger than going through U, right, going to U and then taking this edge, then of course I'm going to update the estimate I have to go to V. And then, right, I'm going to keep track of some parent pointers to reconstruct the path. Okay. All right. Does this operation make sense? Like why this is a sensible thing to do, right? Like clearly, right, this is like a nice thing to do, right? Because you're not going to get worse distances, right? You're always taking better things. And somehow you're like saying, if I can go to my neighbors faster, then I can go to myself faster. That's essentially what this operation is also saying. Okay? Yeah. Yeah, so that's the next step, right? So we're going to apply it to many, many edges. But I'm saying this relax operation, I'm going to just define it for one edge for now, right? So if I give you an edge u comma v, the relax operation says, can I improve the distance to v through u? Okay, that's what this sort of one cog in the algorithm is going to say. Okay, can I make an improvement by using this particular edge? That's what this is saying. Okay, so this is a very like local improvement, right? I'm only looking at one edge and two endpoints. So now this is the magic of this Bellman-Ford algorithm. Somehow we're going to make lots and lots of these local improvements, and it's going to lead to a globally optimal algorithm. Okay. All right. So before I present the algorithm, there's just one small piece. Any questions like what this operation is doing? Hopefully it makes sense that this operation never hurts, right? It seems like a sensible thing to do. If you're confused why this operation is interesting, like that's a good time to ask a question. Okay. All right. Like I said, it's just making local improvements. right? The thing about this local improvement is that there's one thing to check, which we'll get to later, but I'm just going to say it now, which is this local improvement, right? Essentially, what's going to happen is all the distance estimates I have will never be like magically great. They'll never undershoot, okay? So we'll get to this later. This point doesn't matter now. But okay. Right, so I told you there's a way to do this local improvement that kind of improves my estimates over time. The question is, right, which edges do I pick to make this local improvement on? And what is the order in the order in how I pick the edges, okay? So that's the, right, that's not so clear, right? I just told you, if I give you an edge, there's a way to improve it, but how do I pick which edges to improve? Which order do I look at the edges in? Okay, so the entire Bellman-Ford algorithm is the following, okay? I'm going to look at all the edges. I'm going to label them 1 through m, okay, in some order. It doesn't matter, okay? But I'm going to fix an order, okay, of the edges, okay? Then I'm going to relax the edges in that order, okay? What does relax mean? We do that operation, right? If I say if I can go to that endpoint faster by hopping through the edge, then I update it, okay? And I repeat this entire process n-1 times, but I keep the order the same, okay? So that's the Bellman-Ford algorithm, right? I do this like local improvement for every edge once, and then I repeat the whole thing n-1 times, okay? Of course, it's like not clear why this is correct, right? It's like I'm just doing some local improvements. But what we'll show in a bit is that if you do this, right, the source is fixed, then this will give you the shortest path from that source to all the other nodes, okay? At least does the algorithm make sense, okay? So all I'm doing is this local update for every edge in some order, and I'm repeating the whole thing n-1 times, okay? Does the algorithm make sense? This is the entire algorithm. Very easy to code, but it's kind of magical in some sense. Okay. Any questions? And we'll see an example on the board in a bit, like maybe very soon, actually. Any questions about the algorithm, the relax operation? Right. Okay, so that's the entire algorithm. Of course, it's not clear why it's correct, so we're going to prove that. But what is the running time of this algorithm, right? Yeah. Yeah, right? It's like I'm going through all the edges once, that's O of m time, and I'm repeating this entire loop n times, O of n times, right? So it's O of mn. Of course, I'm hiding the fact that, okay, like at some point we need to handle negative cycles that have negative weight, right? Then I can go on and on them. So we're going to handle that also. But yeah, so this is the entire algorithm. Before I prove to you why it's correct, let's see an example, okay? So how to run this algorithm. So I'm going to go on the board, but before I do that, any questions? Relax operation. Yeah. Yeah, any ordering is fine, but you have to fix that ordering in all of the n loops. So in the beginning, you can take any order of the edges, okay? But that order has to be the same in the n-1 loop, okay? Yeah, that's the cool thing, right? We're going to prove that no matter how you order it, as long as the order is consistent, it will work. And the fact that you do it n-1 time is also very important. If you do any time less, then it won't work. And also, like, I mean, this is something you can play around with, actually. If I change the order in how I relax in between the loops, it also won't work. So the fact that you have to do this in a particular way is very important. And we'll see that in the proof, like where it comes up in the proof, that you're using the same ordering, okay? Or like, we'll see actually in the proof why like n-1 times is really important. If you do a little bit less, it's not going to work, okay? But before I do that, right, let me go to the board, and then I'll show you how the algorithm works in an example graph, okay? Okay, so we're going to go to the board. Okay, this is still my board from last time. Okay, so now let's delete this. Okay, so now let me draw a graph. Okay. Okay, so this is my source node. Okay, give me like a couple minutes. A, C. Call it E. And then let me add some edge weights. Say this is 5, this is -2, this is 2, 4, 4, 1, -1. Okay, so now let's do this. Now let's do this in real time. Okay, and the order of the edges. Let's say we go left to right and top to down. Okay, so this is the first 3, the next 3. And then the last 3, okay? So that's the order that we're going to fix. Okay, so initially, right, the distance to the source is 0. Let me see if I can use a red marker. Okay, so distance to the source is 0, right? Initially, everything is infinity, okay? Okay. And you kind of see like somehow the 0 is going to propagate throughout the graph. That's what's happening, right? Initially, right, I know the distance to myself is 0. And somehow I'm going to propagate it throughout the graph. Okay, so that's what this algorithm is doing. So now let's do the first run, right? So now we say, OK, well, it's right. I relax this edge. Well, I can go to this 0 cost. This is infinity. So of course, it's better to go to 0 and 5. So this gets updated to 5, right? And now I relax this edge. Well, right, it's infinity, but if I go through here, right, I get 5 plus 1, so I get 6. And then I relax this edge, and then now I get 9. Then I relax this edge. Well, it doesn't do anything, right, because I haven't reached here yet. It's still infinity. This one, that doesn't help. For this one, right, if I relax this edge, well, it's infinity, but if I go through B, I get 6 minus 1, so I get 5. And then let's say I relax this edge, right? I'm doing this way, this way, this way. So now I relax this edge, right? Then I get -2. This edge, this edge. Well, it's currently distance 5 to get to D. But if I go through this node and take this edge, then I get 2, right? So I get 2. And now I relax this edge. Currently, I know it's distance 9 to get to E. But if I go through D and take this edge, right, then I get 3. Okay, so that's one round of relaxation. Okay, so right, so how I relax is right. I did the top edges, then the bottom, then the middle 3, and then the bottom 3. Okay, so that was one round. Okay, does that make sense? Like how that worked? Okay, so it's like somehow this 0 propagated throughout the graph. By saying, OK, I know to get to myself is 0, but if I take this edge, now it's 5, and so on. OK, that's one round. Now I have to do this like a few more rounds. OK, maybe I'll do it one more round, and then I'm done. OK, I'm not doing it anymore. But at least the first round, did that make sense? Like how all the numbers got updated? Yeah.
We only go like the most direct path. Like, let's say for like from S to A, we can go from -2 to -2. Do we not do that in first when we're starting from S?
No, right? No, yeah, because right, the whole you have this huge graph. You don't know what the most direct path is, right? That or like even the things that take the fewest number of hops is not necessarily the best, right? Here I take 2 hops. That's better, right? But somehow this algorithm is going to slowly discover it, right? That's why I do this relax operation many rounds, and that's going to propagate throughout the graph. Okay, so now that was just the first round, right? I told you I had to do this like 1, 2, 3, 4, 5 rounds in total. Okay, and -1. Now let's do this again. Okay, now let's keep the order. Okay, let's relax this edge. Well, nothing really changed. Okay, blah, 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 right? I mean, no, but like, let's go to the interesting part, right? At some point, I'm going to relax this edge, right? Now look what happens, right? I know from the previous round to get to C, it's -2. Currently, my distance to A is 5, right? But instead, if I go through this, if I go use this edge, then this is going to update to 0, right? In the second round, okay? When I end up relaxing this edge, okay? But I'm not going to do all the things, but you see how like progress is made? Like somehow, you know, in the first round, maybe you don't find the best way to get to places, but then in the second round, you get some improvement. Third round, you get some improvement, and so on, okay? All right? Yeah. And, you know, I mean, you have to do this like 5 more times, right? Which I didn't do, but does that make sense, like how these numbers were updated? Right? All I did was I looked at my current estimate. If I have an edge, I look at my current estimate on both endpoints and say, OK, to get to here, can I instead go through here? And if I can, if that's a better choice, then I update it, OK? OK. Any questions? I mean, I still haven't, I mean, it's still mysterious, right, why it works. OK, but at least like in this example, any questions like how these numbers came about? OK. All right. OK. So now let's prove that this algorithm works, OK? And kind of here's a hint, right? Which is why is it working? Is like we only discovered this way in the second round, okay? Not in the first round. So essentially, what's happening is that every round, you're discovering paths that are longer by 1 hop, okay? And of course, if you do n-1 rounds, you're discovering paths that are as long as n-1 hops. So then that's why you're done after n-1 rounds, okay? So the main thing is this lemma, okay? After I iterations of this, like, you know, the outermost loop, right, where I'm relaxing all the edges, the distance to all the nodes, the estimates that I have, is less than or equal to the shortest path from S using at most I hops, okay? So that's the main thing we're going to prove, right? After every iteration, I have this, you know, after iteration 5, I've discovered the shortest path to go from a source to that node using at most 5 hops, okay? So that's like the main lemma, right? We're going to prove for every iteration, I've discovered all the shortest paths that use that many hops, okay? All right, so that's what we're going to prove. Any questions, right? Kind of to see here, right? Like after the second, like the first round, right? I only discovered this 1 hop path, but in the second iteration, right? I discovered this 2 hop path. So that's essentially what's happening. Is like for every node, after I iterations, I discover all the paths essentially that have at most I hops. Okay, so the way to quantify is like after I iterations, the estimate that I have is smaller than the estimate that I can get using paths of I hops, okay? And then 1, 2, 3, 4, you know. That's why I do n-1 iterations. But that's what I'm going to prove, okay? Questions about the statement, like where it's coming from? What it says? Okay. So the proof is just by like picture, okay? So let me just draw the proof, okay? So I have some node, I have the source, right? And I'm interested in some node V, okay? And then what I do is in my head, okay, this is a thought experiment, this is a proof, right? I consider the shortest way to go from S to V using I hops, okay? So it's using I edges here in this path, okay? That's the best way, let's say, in my head. My goal is to say after I iterations, I've discovered this. Like my estimate is better than this, or at least as good as this, okay? Why is this true? Well, I'm going to prove this by induction, okay? So right, of course, the first step is, okay, none of the, the only paths of hop 0 are the to itself, right, which is 0. So so now I'm going to prove this by induction. So then I say, okay, consider the node u, right? That's right before node v, okay? In this best path of length I, of hop I. Well, to go from S to U, right, this path uses I minus 1 edges, right? By induction, the distance to U at this point is at least as good as this, right? So then when I relax this edge in iteration I, I'm going to discover going to here and to here. So that's the proof. Okay? So almost like we didn't do any work. Okay? So just to summarize, right, how do I know that after I iterations, the distance to V that I have so far is as good as the best way to go from S to V using I hops? Well, I consider the best way, right, in my head, right before I get to V, right, there's a node U, right? This path is actually the best way to go from S to U using I minus 1 hops, okay? By induction, I've already discovered that for U dot D, right? And when I relax this edge U comma V in iteration I, the distance I'll update for V is this distance plus this edge, okay? So it's almost like we didn't do any work, right? So it's kind of magical, right? It's like saying the best way to use 5 hops is to look at the best ways to use 4 hops and take one more step. By induction, I've already found all the best ways to all the other nodes using 4 hops. And then in the relaxed step, right, in iteration I, this is one choice I can make. So of course, I'll do at least as good as that, okay? Okay, so that's the entire proof, okay, of this. Okay. Any questions? But if this doesn't make sense, just think like the invariant that we're keeping track of is after I iterations, I find the best distances using I hops. Okay, so now how do we complete the proof, right? So there's one more step, which is, well, we have to argue that n minus 1 iterations is enough. So let's see why. I'm going to delete this. So then kind of to complete everything, we have the following, let's call it now theorem, okay, which is, so the theorem says this, okay, if G has no negative weight cycle, then Bellman-Ford is done after n minus 1 iterations, okay? All right. So that's the thing. And then, so how do I use the lemma? Well, I say, okay, if the graph has no negative weight cycle, let's assume for that for now, then any shortest path from S to any node is going to use at most n minus 1 hops, right? Because if it use more hops, then it's going to have to repeat a vertex, which means there's a loop, right? But why would I need the loop, right? I'm assuming there's no negative weight loop, so I can just like cut out that loop, right? Okay. So the proof is the following, right? Shortest paths are simple, meaning they don't like repeat any vertices, okay? If you assume there's no negative weight cycle, right? So the proof is, let me draw it here, right? If somehow to go from this node to this node, right, I was going and then I made a loop and then I went again, right? Well, I can just like, at this point, I don't have to follow the loop. I can just go this way straight instead. Okay, so that's why shortest paths are, they don't like repeat any vertices. Well, then, right, if shortest paths are simple, then that means like, the number of hops is at most, right? At most n minus 1, okay? Well, then now we're almost done, right? So that means by this lemma, after n minus 1 iterations, the estimate we have is even as good as the best estimate. And right, the previous thing I said on the slides is you're never going to say something smaller than the best estimate. Okay? And the reason is you only update these values when you actually have a path, right? That's why we did this relax operation. So essentially, right, we just take this lemma and plug in I equals n minus 1. And this lemma says, right, after n minus 1 iterations, Bellman-Ford finds the best path using n minus 1 hops. The shortest path also uses at most n minus 1 hops. So that's why Bellman-Ford is correct. Okay. So this is, of course, assuming there's no negative weight cycle, okay? Because if there's a negative weight cycle, I can go, the path is really long. I keep going, over and over again. But let's assume there's no negative weight cycle for now, okay? So assuming that, does the proof make sense, or at least somewhat make sense? Right, just the main takeaway of this is after I iterations, Bellman-Ford is going to find all the shortest paths of hops at most I, okay? Essentially, that's what it's like maintaining, okay? Any questions, concerns, comments? Okay. Now, there is this one thing, right, which is how do we take care of negative weight cycles? That's really bad, right? Because that means like shortest paths are not really defined. I can go on a loop over and over again, okay? So that's the last thing that we need to do to take care of. But the claim is that if Bellman-Ford doesn't work, it will also tell you if there's a negative weight cycle, okay? So we need to do one modification. Before I do that, I'm going to, of course, go on the board. I didn't make slides for that. But any questions about the proof? Now is a good time to ask before it's gone. Okay, so somehow we have to deal with these pesky negative weight cycles, right? Because if we have negative weight cycles, the proof doesn't really work, because the negative weight, the way to go from some node to some other node could be very, very long, right? Just keep going around and around, right? So how do we deal with negative weight cycles? So there's two ways. I'm going to talk about one way, okay? And there is one more way in the notes, so you can take a look. But the idea is very simple, okay? Right? The way I said Bellman-Ford is I do n minus 1 iterations of this relaxing operation. What do? Is I do one more round of relaxing operations, n iterations of it. And if I notice that the distances are changing, then that's going to tell me that there's a negative weight cycle, okay? So the idea is if there are no negative weight cycles, then after n minus 1 iterations, the distances should be stable. Nothing should change. So I do one more round of this relaxing operation, and if I notice things are changing, then that's going to tell me, hey, there's a negative weight cycle. Something is fishy here, because the proof said I should have been done. Okay, so that's essentially the idea, which is just right. So how do you check for negative weight cycles? So how to check for negative cycles? Okay, basically do one more round of relaxing. And the claim is that if there's a negative weight cycle, something will update, okay? So the claim is that some v dot d will update, and that will tell you there's a alert, right? This is a part of a negative weight cycle. Okay, negative weight cycle. Okay. So just to summarize, right, we should have been done after doing n minus 1 rounds of relaxing. So what we do is we just do one more round and check. Okay. If there's no negative cycles, the distances will all stay the same. The values, none of the values will change. But if one value changes, then you automatically know something is wrong. There's a negative weight cycle. Okay. Why does this work? So let me draw a proof. why this works. Why does this work? The claim is that if there's a negative weight cycle, there's always an edge that can be like, there's always an estimate that can be improved, okay, no matter what. Okay, so that's the claim. So the claim is, right, if there exists a negative cycle, some edge can always be relaxed, no matter what, okay? Okay. And that's bad because, right, previously we proved that if there's no negative weight cycle, after some number of rounds, there's no relaxing you can do. You're already done. But I'm saying if there's a negative weight cycle, the way you test for it, the way you check it is you do one more round of relaxing, something will change, and that's what's going to let you know, hey, there's a negative weight cycle, okay? The proof is like this, okay? So let me just draw it out, okay? Let me just pretend there's 3 vertices, right, in a negative weight cycle. This is vertex 1, vertex 2, and vertex 3, okay? And let's just say for simplicity, they have edges -1, -1, -1, somewhere in the graph, okay? The claim is that no matter how many rounds you do, there's always one of these 3 edges can be improved on, relaxed, okay? Any intuition for why? Yeah.
Or if you just go through the cycle again, get away without it.
That's kind of the intuition, yeah. But that's almost it. But let me just let's just write the math, and then it's a little bit more clear. Let's say that this edge cannot be relaxed, okay? So that just means that, right, this estimate is smaller than, this distance minus 1, right, the weight. And if this edge cannot be relaxed, then that means the same thing, right? v1 dot d minus 1. And now if this edge cannot be relaxed, then that means v3 is less than v2 minus 1, okay? So I'm saying, okay, assume for contradiction that none of these 3 edges could be relaxed, okay? Then I get these 3 inequalities, right? Because if it was flipping the other way, I could relax it. That's the definition, right? If the distance was worse, I could go through here. But then I just sum on both sides, and then I can cancel this, okay? Because it's a cycle, right? Everything appears once. So then I get 0 is less than minus 3, right? Which is a contradiction. So that means one of these inequalities had to have been flipped, meaning that was the edge that you could have relaxed, okay? But I mean, yeah, if this doesn't make sense, just there's another way in the notes, like a different way to prove that Bellman-Ford will find the negative weight cycles. But just at a high level, right, you do n minus 1 rounds of relaxing edges, and then to check, you do one more round, and then something will break, something will like update, and you say, oh no, that's the negative weight cycle right there. And then there's lots of ways to fix it, but you can just say, oh, I don't have to report anything, let's just say, because you detected like negative infinity, okay? Let's say for that, okay? So yeah, in summary, right, if I give you a graph that has both possibly positive n, the negative weights, Bellman-Ford is an algorithm that runs in O of m times n time, and it gives you from a source to all the other vertices the shortest paths. And if you run it, right, if you modify it like this, it will also tell you where the negative weight cycles are, okay? So every edge that can be relaxed is going to be part of a negative weight cycle. And there's another version in the notes where it like more directly helps you find the negative weight cycle, okay? But yeah, okay. But yeah, just assume, right, Bellman-Ford either gives you the shortest paths from a node, or it tells you, here, this is a negative weight cycle. Here it is, okay? Just assume that. You can do that. Okay. Any comments, questions? So right, like, so we, in some sense, it feels like we didn't do any work, but now we have this powerful algorithm, right, that can find single source shortest paths. And in some sense, this is like thought to be the optimal algorithm. Okay. Okay. Any questions before I talk about something slightly new? And also, I'm happy to like go back, review the Bellman-Ford, relaxing, any proofs that we talked about. Okay, so definitely in this homework, right, there are some questions where I think one of the problems is like you have to detect a negative weight cycle, so you run Bellman-Ford. Okay, that's like one of the problems. Okay, so now let's talk about another shortest path algorithm. Okay, now let me erase this. Okay. Now I'll talk about an easier case. So I'm going to talk about shortest paths in a DAG. Okay, so what is a DAG? It's a directed acyclic graph. Okay, basically it's a graph without cycles. Okay, like there are no loops at all, negative, positive, whatever, no loops. Okay, so that's a DAG. How can we check if a graph is a DAG? We talked about this last time. Yeah. But how can we, if I give you a graph, I put yes or no? Yeah. Yeah, exactly. So we do DFS, right? The thing was, if there is a cycle in the graph, what will happen is like when you're in this like execution path of a node, right? You're calling DFS on a node. You go deeper and deeper. At some point, there will be a node that points back to that node, and that's a cycle. Okay, so DFS helps you determine if a graph is a DAG or not. Okay, but now we're in a, now the problem is slightly different. Is I give you a graph, I promise you that it's a DAG, but the edges have weights. Okay, and now I want to solve the single source shortest path problem. Okay, of course I can run the Bellman-Ford algorithm. That's O of m times n time, but we're going to use the structure of the graph to help us get a faster algorithm. Okay. So like I said, right, I think someone mentioned, right, what is the nice property about DAGs is that there is a way to order the vertices such that like if you order the vertices, the ordering is such that a node only appears before or after all the nodes that points to it. Okay, so that's called the topological sort, right? Topological sort, right? And how do you get this, right? You just run DFS from any node, and like the reverse or the finishing times, depending on, right, whether you want everything to point towards you to be before or after, doesn't matter. You're just reversing it. But essentially, topological sort is, right, you run DFS, you look at the finishing times of the vertices, and that gives you a way to order the vertices in a DAG so that, let's say, a node only appears before all the nodes it points to. Okay? All right, that's what we talked about last time. So that's a structure, right? That's very special in a DAG, right? It's not a path graph. It's just like it's a graph without a cycle. But in some sense, it is like a path. Like you can order the vertices from left to right almost. Okay. So kind of like if I have this, acyclic ordering of the vertices, right? That's is there any intuition of like why shortest paths should be faster or easier for this graph? So it's related to dynamic programming, right, almost. It's like shortest paths, and I'll write this on the board. We'll draw some things. But shortest paths have this structure that a subset of a shortest path is also a shortest path, right? The shortest path to go from A to B, let's say go through vertex C. Well, A to C, that part is also a shortest path. So in some sense, right, if I give you a DAG, there's a way to order the vertices. Then you just find shortest paths in that order, right? Sort of like we're going to do dynamic programming, and that's going to be a much faster algorithm for finding shortest paths than in general graphs. Okay, So in general graphs, we have to go back and forth on the edge over and over again. But in a DAG, we're going to be able to go through the edge only once, and then find all the single source shortest paths. Okay. Okay. So let me draw an example. Okay, of a DAG. So here's an example. Okay, so let's say my source is this node, and I have a node here and a node here. I have an edge this way, and an edge this way, and an edge this way. Let's say this is 8, 8, 8. Let me just draw it 2 levels, right? This is a DAG, right? There's no cycle in this graph, right? All the edges are kind of pointing out. And DFS, right, or topological sort will tell me there is a way to like kind of place the vertices from left to right, right, such that a vertex only appears after all the nodes that point to it. Okay, so that's the that's the topological sort. And like, how does this help me find shortest paths, right? Well, essentially, I'm gonna go left to right, and I'm gonna relax the edges in that order. Okay, so I'll be more precise. But essentially, you can kind of see it, right? Like first I go here, then I go here. Oh, that's 8. And then I go here. Well, I can relax here or here. But I pick this one, that's 8. And then I go left to right, and I never have to backtrack because of this like topological sort, right? Like sort of anytime I reach a vertex, I've already reached all the vertices that point to me. So I'm already done with them, right? So I can kind of extend the path one step. Okay. So let me write this algorithm. Okay. So the algorithm is following. So it's the same kind of framework. I do edge relaxation, but just in the topological sort, okay, sorted order. So what I do is for u in V, okay, and then for V in the neighbors of U, I relax U comma V, but then the top thing has to be in, it's not just an arbitrary order, it has to be in this topological sorted order, okay? Topologically sorted, okay? Okay. So it's almost like Bellman-Ford, except now I order the vertices. So what I'm doing is I'm looping from the vertices from left to right in this topological sorted order. For every vertex, I look at their neighbors, and I relax that edge, u comma v, okay? So every edge is only being relaxed once, rather than n minus 1 times in Bellman-Ford, okay? So the claim is that, right, even if this shortest path, even if this DAG has weights, I'm going to find the shortest paths from the source, okay? All right. Okay. So just imagine what this is doing is, right, if I tell you that, right, if I tell you that your graph is a path, okay? If I tell you it's a path, right, it's just, path like this, okay? And let's say this is the source, okay? If I tell you about that, then finding the shortest path is easy, right? I just go left to right. I fill it in, right? I go to here. Like the only way to go to here is go here first, right? So if I'm done with here, and done with here, right? So I go left to right, right? It's kind of like dynamic programming where it is exactly dynamic programming where the subproblems are, right, the shortest path on this topologically sorted order, okay? So if I order the vertices 1 through n, where 1 is like my source, and it's in this topological sorted order, then the dynamic programming subproblems is, what is the shortest path to vertex I in this order, right? And what is like the dependency on the subproblem, right? The shortest path to vertex I only depends on vertices that point to me, right? But they appear before me in this topological sort, right? So by dynamic programming, right, I'm already done with them. Okay, so that's the entire proof, actually. Okay, so let me write why does this work. So one caveat is, right, you have to do DFS starting from the source so that it's like the first vertex in the topological sort, okay? But right? Why does this algorithm work? Right? The proof is just exactly like I said, right? Okay. Okay. Let's say I care about some vertex v, right? The shortest path from the source, right, to some vertex v. Okay. So the proof is by induction on the place in the topological sort. Okay. So initially, right, S is at the first place in the topological sort. I'm done, nothing to do. So now I'm saying I'm at, let's say this was the 10th place in the topological sort. Okay. What does that mean? Okay. That means, right, how do I get to this vertex v, right? Well, I have to go through some, in the intermediate, right, I have to go to some vertex, let's say u1, or some other vertex, u2, right? But the property of topological sort is I'm going to visit these first, okay? I'm going to visit these first. And the induction hypothesis is when I visit a vertex, I'm done with it. So by the time I get to v, I'm already done with finding the shortest paths to all the vertices that point to v. Okay, that's my induction hypothesis. That's why induction is so powerful, right? It's like you're not doing any work, you're just doing one step, and then it kind of fills it in for you, right? So by the time I get to v, right, well, I need to go through some other vertices. Well, I'm already done with them because they appeared before me, right? That's the definition of the topological sort. Right? And then to get to v, right, I have to go through one of them. I already know the shortest paths to all the things that point to me. And when I do this relax operation, I'm going to take the best one. Okay? So that's the entire proof. Essentially, right, at a high level, what's happening is you're pretending the graph is a path, and you're going left to right. Okay? And topological sort allows you to pretend the graph is a path because it lets you order the vertices so that a vertex only appears after all the vertices that point to it or that depend on it. Okay? Right? That's the entire proof. Yeah, and then running time here is only, right, I'm only going through an edge once, so it's actually just O of m plus n. Okay? So it's a very fast algorithm. Okay? But if this doesn't make sense, just think if I tell you the graph is a path, okay, obviously the thing to do is go left to right, okay, left to right. If I tell you graph is a path, the source is at the left end, we just go left to right, right, filling it in. Another way to think about it, it's like dynamic programming, right? The distances to v only. How do I get to v, right? Well, I have to go through a vertex that points to v, and by the way I'm going to set up my subproblems is I'm going to visit those problems first. So by the time I go to subproblem v, I'm already done with all the subproblems that point to it. So then I take the best one, right? I do the relax on all the edges. So that's another viewpoint. So whichever helps you, like topological sorting, dynamic programming, or just pretend it's a path, right? If it's a path, I go left to right. DAG are almost like paths, okay? Yeah, so that's it, right? So now, in summary, right, what do we do, right? We covered two algorithms. One is this Bellman-Ford algorithm, very powerful, works for any graph you want, any weight, positive, negative, directed, not directed. Just here's a note, right? If your graph is undirected, you can just make it directed by adding two edges, okay? But yeah, Bellman-Ford works. For any grading, it's very powerful, but it's also kind of slow, right? It's m times n, and if m is n squared, that's an n cubed running time. But if the graph has a special structure, like it's a DAG, right, you can take advantage of it. And the next class, we're going to take advantage of another special structure. If the graph only has positive weights, then you can also do something much faster, okay? Yeah, so that's it. I think I have 15 more minutes, so if you want to quickly chat about, well, I mean, not too many of you, but if you want to quickly chat about your test, I'm also here, okay?